Do this. The production and properties of X-rays, and we are still figuring out. I got to bring the clicker, so I'm gonna stand, but I'm gonna stand over here so I'm close. All right, do y'all want the lights dimmed a little bit? Take some of that glare. Better? Yeah. Thank you. All right. And the construction of the tube. I want to make sure that okay. Just want to make sure I had the audio on. Technical difficulties last week. Okay. So we have two sides to the X-ray tube. And if you had RAD 107, then you're going to have already heard of these terms, anode and cathode. So anode is the positive side of the X-ray tube. The cathode is the negative. So you can remember it easily. A plus, we want A pluses. I mean, C minuses will do, but we'd rather have A plus. So the anode is the positive side. The cathode is the negative. So we're going to break down the two different sides and talk about the components of each. You may have already looked at some of this in the lab manual. There was some labeling in there, so you could go ahead and get started on that if you wanted to. So this may be a little familiar to you. Hopefully you did your reading. But the parts of the cathode assembly are the filament, which is made of tungsten, the focusing cup, and then associated wiring. And then the anode assembly is going to include the rotor, which causes the anode to rotate. It's activated by pressing the exposure switch on the console. So if you remember being in the lab, halfway, when you press the exposure button halfway, you can hear it start to spin. Come on in. And that's what you're hearing when you hear that first noise. When you go halfway down on the exposure button, that's the rotor starting to spin. So the anode, we also have the disc right here and the stem, which attaches it to the rotor. So if we took that disc off and we were just looking at it, and I actually have some examples of these in the lab if anybody's interested in actually seeing what one looks like. It's made of tungsten as well. It's alloyed with rhenium, molybdenum, and graphite, which makes the anode lighter and easier to rotate. So you can just see the cutaway and see the different layers of the disc of the anode. The focal, so this would be looking at the disc on end. So if I was holding it up and we were looking at it straight on, you could see the focal track, which is around the circumference of the disc, and it has a beveled edge, which means it has like a slight angle around the edge. And again, let's see if you can see that. See, this is what we're talking about, this beveled edge right here. So the focal track is this entire area. This is the area of the disc where X-rays could possibly be produced. It just depends on where the electrons strike it. And so the focal spot is going to change as the anode rotates during the exposure. So any of this area is a possibility of X-rays being produced, but where they are actually produced, is where the electrons interact with it. We'll talk about that a little bit more here in a minute. That's called your focal spot. So when we are, okay, we'll get to that more in just a minute. When we are setting the focal spot on the control panel, we've talked just briefly about that. Large and small focal spot, that's what we're talking about. How big is the area going to be on the focal tract where the x-rays are produced? And again, that is related to how big the filament is. So in just a second, we'll look at that dual type filament tube. The tube envelope or envelope surrounds the cathode and the anode. Virtually all of them use metal enclosures now instead of glass, but you may still see some x-ray tubes out there that are glass. And Ethan has some examples of old tubes that have been taken out of x-ray machines. And so he generally shows you those in your physics class. But there is a window in that is very thin spot below the anode, and that's where the x-rays leave the x-ray tube. Okay, so the window is the only area that we really want the x-rays to leave the tube, because those are going to be the useful or the primary being that is directed towards the patient. So all of that whether it be glass or whether it is metal enclosing the anode and the cathode, all of that is also housed within this metal housing of the whole tube component. From the ceiling, we have the ceiling mounted. You may have floor mounted. When you're out there in clinic, there's a couple of sites that have the tube mounted from the floor, so not quite as much flexibility as we have, where we can, drag the x-ray tube all over the room. So again, this area here is the housing. It does a couple of things. It protects your tube, and it also acts as a shield. So it absorbs radiation that's produced, except those aimed at the window. So there's always going to be some leakage radiation, but it's very minimal. Because of the either glass or metal that's surrounding the anode and the cathode, and this extra layer of metal that's the housing itself. So other things that are part of the metal housing are the electrical insulation, and that helps to transfer or dissipate heat. So we're going to see in a minute that there is a lot of heat produced in the production of x-rays, and so there has to be some way to sort of dissipate that heat production. So let's look at the actual chain of events that is required for the production of x-rays to occur. And so we can pretty much say, some books say 4 steps, some just sort of condense them into 3, some stretch them out more, but basically 4 things have to happen for the production of x-rays to occur. So you have to have a release of electrons from that filament. So this would be our filament right here. So you can see we have a smaller filament here and a larger filament here. So we choose that when we choose the focal spot. And so we have that release of electrons. We have the focusing of those electrons by the focusing cup. We have to have an acceleration of those electrons going from the cathode to the anode. And then we have to have a sudden stopping of those electrons by the anode. So we're going to look at each part of that series of events or chain of events that has to happen. So the releasing of electrons, there's some basic terminology that you just have to memorize, some very fundamental terms. And thermionic emission is one of those. So I would star that, highlight it, underline it. That is talking about the boiling off of electrons. So that filament, when the current is applied across that filament, so when we start that process of the exposure, it gets white hot or incandescent. So it actually glows, okay? And those electrons are boiled off of that filament. That is called thermionic emission. And it creates what's called a space charge. And that's electrons near the filament after thermionic emission. So you can see, here's your filament. Once that current is applied across that filament, then these electrons are sort of balled off and they create a space charge here. So that's electrons have what charge? Positive or negative? Negative. It's a negative charge. Okay, so that's why the cathode, we say, has a negative charge. And we're going to see in a minute that, again, the anode has positive. So that push-pull effect is what helps to accelerate those electrons across the tube. So we want to focus those electrons. We don't want the electrons just all willy-nilly in there. That's not very efficient or, productive. So the basic function of the cathode is to expel the electrons from the electrical circuit and focus them into a well-defined beam aimed at the anode. So again, we want the focusing cup to sort of wrangle all the electrons in, okay, so that they are not just flying around in there, not being efficient or productive. So here we are talking about the dual focus X-ray tube. Now, some of your equipment out there may have 3 focal spots. All the ones I ever worked with only had 2, but there's some, you may see that option on some of your equipment, whether it is actually set up or not. It may have the icon there as if you could choose it, but it may not really be there available to you. Most all of them are going to have two filament sizes, small and large. And so which one do you think is going to be able to handle more heat, the small or the large? The large, of course. So that's what's going to help us decide, which focal spot do we need to choose when we're choosing on the control panel. So we've talked about the boiling off of the electrons. That's the first thing. We talked about the focusing of the electrons. That's the second thing. The third thing is acceleration of those electrons across the X-ray tube. So we have high-speed electrons. We have that push and pull effect going on because what do opposites do? Attract, right? So we have those electrons and the positive side of the anode. It creates this push and pull due to the magnetic fields. And so the electrons are sort of repelling each other and the anode is trying to attract them. So that's what creates this acceleration of electrons from the cathode over to the anode. And then we have to have sudden deceleration of those electrons or a sudden stopping of electrons. And so when that occurs, it converts kinetic energy of those electrons into, look at how much heat. That's a lot, right? Only a little bit less than 1% or about 1% is actually going to be X-rays produced. So a lot of heat has to be managed in the X-ray tube. That's why we have the insulating oil that's a part of that housing. And so it's not a very efficient process, is it? If only 1% of those electrons are turned into X-ray photons. A photon is a bundle of energy, but it's all we got. It's been that way for, since 1895 when Röntgen discovered the X-rays. So there's a couple of interactions at the target that we are just going to just briefly introduce, just so you sort of have an idea of what is happening actually at the target in the anode. Ethan will break these down more in your physics class. And so I believe that won't be until this time next year for y'all. The curriculum is being in the process of being changed. But anyway, so we're just going to briefly talk about these a little bit just to sort of get you used to the terms and somewhat understand what is happening when those electrons suddenly hit that anode target. So Bremsstrahlung or braking radiation, Bremsstrahlung is a German word. The electrons from the cathode are attracted to the nucleus of the tungsten atom, so the tungsten that the disk is made of. Those electrons slow down or break and change direction and lose energy. The lost energy is released in the form of an X-ray photon. Again, a photon is like a bundle of energy. And that's the primary way that the X-ray photons are created at the anode target. So the majority of the X-ray production is created through bremsstrahlung. Okay, breaking. That's what bremsstrahlung means, is breaking. Characteristic is a very, very small percentage of the production. So electrons from the cathode collide with the inner shell electrons in the tungsten atom and sort of knock it out. And then that leaves a hole, right? It leaves a vacancy, and we call that ionization. That's another term we're going to deal with. Here's ionization. So an electron from an outer shell sort of falls in to fill it and releases energy in the form of an X-ray photon. So again, most of the production of X-ray is going to be through the breaking radiation. This is a very, very small percentage, but you do just need to understand those two terms, and we'll get into those in greater detail later. This week in your RadTech boot camp assignments, I believe, let me look really quick, there's the videos on those two things, and I love those videos. I think they make it just a lot easier to visualize. Let's see here. That is maybe I didn't put them in there. Anyway, they are available in RadTech Bootcamp. I'll have to look and see, make sure of when because I've added this. We rearranged the curriculum just a little bit, so I felt like I needed to touch on it a little bit in my class. We used to teach physics in the first semester. Can you imagine having physics on top of what you got now? That was rough. So we moved it, but now we're going to move it back to the second semester, just because we feel like you need to introduce before your fourth semester. Okay, so isotropic emission. That means that the X-rays that are created, they fly off in all directions uniformly in a sphere shape. So, but only the ones that are aimed at the patient are useful. So this is why we have the tube enclosure and the housing, just to prevent leakage radiation. Because the only photons that we're interested in are those X-ray photons that are down here, right around in here, that are going to come through the window of the tube, enclosure and be directed at the patient. So those photons that exit that window and they're directed at the patient are called primary. That's the primary beam. Okay, those are the useful photons that we're interested in, because those are the ones that are directed at the patient. These other ones that may fly off in other directions, they're of no use to us. Okay. So some properties of X-rays. They are invisible. So we're going to actually look at each one of these specifically. So they are highly penetrating and invisible. So they act similar to light photons, but instead of just being reflected or casting a shadow, they actually go through the patient or depend on their energy. But they are invisible. You cannot see or feel them, no matter what the patient says. They do not feel the X-rays. I had a patient tell me they felt the X-ray one time, and I didn't want to argue, but no, you did. You may have felt the pain from a certain position or projection, but not the X-rays themselves. And if we used to do an example, we would go in one of our rooms that had no windows, and we would close the door, turn the lights off, and open up an old CR cassette and irradiate it and let you see, what would happen to that cassette when it was exposed. And you can't see the X-rays themselves, but you can see the result of them interacting. It's just like the wind. You can't see the wind itself, but you can see the effects of the wind. It's the same thing with X-rays. They travel at the speed of light. So that is the reason you can walk immediately back into the x-ray room. So as soon as you make the exposure, you can walk right back in. They're not still flying around in there. So you do need to know that the x-rays travel at the speed of light. They are heterogeneous or polyenergetic, which means they have many different energies. We will get into this more a little bit next semester, and then Ethan will get into it even more with his physics. So that just means that when we set the kVp, we're setting the kilovolt peak. So that is the peak energy that the photons can have, but that doesn't mean that every photon is created at that energy. There's many, many different energies. They do travel in straight lines, and they do diverge from a point source, which affects our source to image distance, the alignment of the part that chooses the IR, the patient's dose, receptor exposure. So patient dose and receptor exposure are two different things. They're similar, but the patient dose, of course, is how much radiation is the patient actually getting. Receptor exposure is how much dose is the receptor getting. So that's the amount that has made it through the patient and actually interacted with the IR. They do cause some materials to fluoresce. And so this is what I was talking about when I said we used to open up the, see, I should have kept one of those. There may still be one over there. I might have to see if I can go back sometime and get it so I can show you. But when we would shut out all the lights and we would open that cassette and we would irradiate it, you could see a light that was given off when the x-rays interacted with that plate in there. And so that's what we mean when we say cause some materials to fluoresce. This also is related to the scintillators that are in the DR detectors. So the detectors that we have in the lab have scintillators in them, which means, again, when x-rays interact with them, light is given off. And so light is what helps create that image. And of course, they affect radiographic film. That's one of the reasons why we have radiography, is they realized, hey, this is a medium that we can actually see the inside of a patient without cutting them open, right? Because it does affect radiographic film. They do produce scatter radiation. So this is when your x-ray photons interact with matter or interact with the patient, and they change direction, and then they have less energy. We'll get into that more in RAD 114. But here you can just see from this picture, here's your primary beam that is coming from the x-ray tube being directed at the patient. And so those photons, so these are x-ray photons that are coming towards the patient. They can either pass all the way through the patient to the IR, not interact at all. They can totally be absorbed in the patient, like in areas of like bone, or if they have some kind of metal prosthetic, if they've taken barium in, like you're doing some kind of stomach procedure or something, or they can interact, lose energy, and change direction. And those are called scatter photons. And those are the ones that we do not like. They are a part of imaging. We have to deal with them, but those are not the photons that we want to reach the IR, because they're not an accurate representation of the anatomy. And they can cause biological damage. So the x-ray photons can change the atoms in a living body by causing electrons to leave some of the atoms in the body. This is called ionization. This is another term. There's just a fundamental term that you need to know. So when an atom loses an electron, it becomes ionized, and that's when biologic damage can take place. So we say that that damage is possible with any dose. We just say that. Okay, it's probably not really true, but we don't exactly know for sure. So that's why we have to be careful about protecting ourselves, patients, and others from unnecessary radiation. So we just assume that any dose might be harmful. So that's why we say ALARA, as low as reasonably achievable. Keep doses as low as you possibly can through different means, shielding the patients when you can, collimating in so you're not exposing the whole, room, wearing lead aprons when you are in, if you have to be in a room during a procedure or something, stepping back 6 feet. There's a lot of things. Time, distance, shielding. Those are the three. Y'all probably did the video on cardinal rules. So time, distance, and shielding. Okay, so that's the first PowerPoint that we needed to go through. Do you have any questions related to any of that we just went over?
Is the isotropic emission in Faber?
It may not be.
Okay.
That term is a little bit older. I'm not sure why it wouldn't be in Faber, but that actually came from a Wallace book that I used to teach out of.
Okay.
So it may or may not be in there. I'll have to look. Does anybody have your Faber in here? Yeah. You can look in the index and see if that term is in there.
But it's not interchangeable with thermionic?
No.
Okay.
The thermionic emission is just that boiling off of the electrons off the filament to create that space charge, that space cloud. And then isotropic emission is when the electrons have crossed over from the cathode to the anode and actually interacted with the anode, and then you have photons, X-ray photons, and that's what's created in a sphere. But only the ones that come out the window are the ones that we are interested in. One thing that is not in here, but I would like you to know is that, and I'm not sure, I must have rearranged some things and maybe forgot to put it back in there. Within the X-ray tube itself, okay, so whether it be a glass enclosure or metal, a vacuum is created. So it's generally, if it's a glass tube, it's baked until it's created a vacuum in there. Why do you think that would be important, that there be a vacuum within there?
So the electrons can flow more easily or faster?
Yes, I mean, not faster, but so that they don't have other things to what until they get over there to interact with, right? So we don't want other atoms in there because that's going to make it less efficient, right? So what you said is true, except for the speed. It doesn't change the speed, but it does change the efficiency of them. So we want it to be a vacuum in there so that it is as efficient as possible, because we already know that it's not very efficient, right? Only 1% or less of those electrons' energy are going to be converted to X-rays. The rest is going to what? Heat. Heat. Yeah. Good questions. Anything else related to production and properties? Okay. Let's share. Okay, so now we're going to move on to the overview of the primary exposure factors. So what are the primary exposure factors? This is good review for section 1, who will have a quiz today, right? Section 1 has a quiz. The other 2 sections have already taken it and they survived. So that's good news. So what are the primary exposure factors?
SID,
SID,
KV,
KV,
speed,
MA, and time. So KVP, MA, time, SID, or the combination of MA and time together as mass. So a lot of your machines are going to, you're just going to set mass. That I used to, when in our other lab setup, we broke everything down into MA and time in my lab when we were learning about technical factors. It's a little harder to do that now with this Siemens equipment because you can't even set MA. All right, and we're going to do an activity next week, and you'll sort of see what I'm talking about. But if you remember, when you're setting the control panel, we have a selection for mass, right? And then it's the next selection is for time. There is no MA station available for us to set. So what's happening in the background that we can't see is the MA is adjusting depending on the mass and the time that we set, because it takes MA and time to make MAS. We're going to look at that. So those are the primary exposure factors. Which one of them is not set at the control panel? SID, because that's set in the room. Source to image distance, the source of those x-rays to the IR, source to image distance. One other thing that I wanted to mention is, if you notice, maybe you have or maybe you haven't, because y'all have a lot of things to notice over the last, can y'all believe this is week 3? It's just, it'll go by fast. But when you pull the tape measure out, have y'all noticed that it doesn't start at 1? What does it start? About like 11, something like that. So why is that? When you pull the tape measure out, the first number down here at your fingers when you're pulling it out is not 1, it's like 11. Why is that?
10 inches with the x-ray tube.
Yeah, so it has to take into consideration from where the measuring tape pulls out to where the source of the x-rays actually is, which is about 10 or 11 inches difference. So that's why it doesn't start at 1. So let's talk about these individually. We have MA, milliamperage. So this is a unit that's used to measure the tube current, the number of electrons flowing per unit time between the cathode and anode. So next week, I believe it is, we will actually really dive in to, let me look at our, yes. So next week, we're going to really dive into MA time mass. Okay, so this is just going to be a brief introduction here. But milliamperage is the current, is setting the current that's going to be applied across that tube, across that filament. All right. So it determines the amount of thermionic emission, which determines the space charge, which determines the number of electrons available. So the current is going to affect thermionic emission, which is the boiling off of electrons. I'm going to keep repeating these terms so that hopefully we're reinforcing them. It determines the number of electrons that are created, that are sitting there in that little space charge, waiting to, accelerate across the tube. So the larger the MA, the what? More or less electrons? More. So 200 MA opposed to 400 MA, 200 is not going to create as many electrons. 400 is going to create twice the amount of electrons, because we're going to learn that it is a directly proportional relationship that MA has to the number of electrons that are created, which in turn affects the number of photons that are created, which in turn affects receptor exposure. So all of these things have relationships, and that's what we're going to learn. However, the current or the MA does not affect the quality or energy of the x-rays produced. It only affects the quantity, the number. It doesn't change anything about their quality. And when we talk about quality, we're talking about the ability, the penetrating ability of that photon. How energetic is it? Okay. All right. So I sort of already said this, but let's look at it again. So the higher MA results in more electrons that move from the cathode to the anode. The more electrons, the more X-ray photons produced. The number of X-rays produced is directly proportional to the MA. The more photons produced, the more receptor exposure. So this is what I literally just said. Sorry, I didn't realize it was on the next slide. So MA to the number of electrons, number of photons, number of photons that reach the IR, which is receptor exposures, all directly proportional. It's a directly proportional relationship, which means if MA increases, all of those things are going to increase proportionally. Okay, so that's something else you've just got to learn. You're going to have, in my class, there are tons of relationships that you have to learn. And I don't want to say memorize, I want to say learn, because I want you to actually understand them. Memorizing stuff in this class is not going to do you any good. You got to understand the concepts behind it, because we're going to continue to build on all this stuff as we go throughout this semester and then into the next semester. Any questions about MA? And there's next week, so not this week, but the next week, you have some very good RadTech Bootcamp videos that describe MA and time and reciprocity. So I love the video on MA and RadTech Bootcamp because it uses the example of a river and current. So to me, it's just a very good visual, a very good explanation of that. All right, so exposure time is pretty straightforward. It's the actual time that the tube current is allowed to flow from cathode to anode. So how long the exposure lasts. So it just makes sense that the longer the exposure time, the greater the quantity of electrons that will flow from cathode to anode, right? The longer it stays on, then the more photons you're going to have produced. Okay? You can sort of think of it as a water hose as well. You know, if you just barely turn the water hose on, it's going to take you a while to fill the bucket up, right? But if you turn that hose on, you get that current flowing greater, then it's not going to take as long, just because you're going to have more water, right? So same thing here. If you have and that would be an explanation of MA. The time would be how long do you have the water turned on, right? So you can always sort of try to come up with examples. I'll try to come up with like everyday examples to help explain some of these concepts. But if you ever, you know, think of something and it makes sense to you in that way, please share it, because a lot of times it'll help, vet it through me, and we'll make sure that what you're saying makes sense. But a lot of times, those kind of things will help you remember stuff. So again, the number of X-rays produced is directly proportional to the exposure time. So again, if the exposure time stays on twice as long, what's going to happen to your quantity of X-rays produced?
It's going to go up twice as much.
It's going to go up twice as much. It's a directly proportional relationship. All right, so when we put those two things together, when we put MA and time together, we get milliampere per second, or mass, MAS, not to be confused with MASS. Two separate things, okay? So MAS is the product of MA and time in seconds. It's simply MA times time equals MAS. That's the formula. That's reciprocity formula, and we're going to talk about that next week. So higher mass results in more electrons that move from cathode to anode. The more electrons, the more photons produced. The number of X-rays produced is directly proportional to the mass. The more photons produced, the more receptor exposure. So all of those things affect each other. So the more electrons due to mass. Now mass can increase with a change in MA. So if we increase the MA, that makes the mass go up, right? Or if we left the MA alone and we said, okay, we're going to make the exposure time twice as long, that also makes the mass go up. So it takes both of those things to make up mass. And when you increase either one of those, then that has the effect of increasing the number of electrons, which increases the number of photons to produce, which increases the number of photons that possibly can make it through to the IR, which is what receptor exposure is. Okay. Kilovolt peak. So it determines the speed at which the electrons in the tube current move. So, I don't think I have it here. It's probably on when we get specifically to kVp, but know that you have to remember two separate things. So you have the speed of the electrons going from the cathode to the anode, all right? And those generally travel at half the speed of light, not the photons. We're talking about the electrons. So before the photons are created, we're talking about the speed of the electrons going from the cathode to the anode is around half the speed of light. Now, exactly what speed they go is determined by the kVp. Okay, so the kVp determines the quality or energy of the X-ray photons produced. So we said that the MA and the time, or the combination of the mass, affected what? Quantity or quality?
Quantity.
Quantity, right? kVp primarily affects the quality of those photons. So the penetrating ability. So let's look at this statement. So the greater the energy of the photons, the greater the penetrability or the ease with which it moves through the tissue. So increasing the kVp increases the speed of the electrons from the cathode to the anode, okay? It also increases the penetrability of the photons that are produced. They're going to have greater penetrating ability. They're going to have higher energy. You're going to learn they're going to have shorter wavelengths, right? So increasing the kVp results in more receptor exposure. Now, when we get to kVp, we're going to talk a little bit more about that because we're going to see that kVp actually affects both quantity and quality. Okay, but mass, so MA time, only affects quantity, number, doesn't affect the energy of them. Okay. All right. So increasing the kVp does result in more X-rays being produced. We are going to see that there are optimal kVps for specific body parts. And so you'll learn sort of ranges of kVp for body parts. And you'll see that those are pretty consistent across the board. I mean, they may differ a little bit when you go clinic site to clinic site, but in general, you could probably use 120 to 125 kVp on a PHS at any clinic site you went to and be okay. Mass is a little different. You're going to see that those vary. It's going to vary depending on part thickness. It's going to vary depending on the type of equipment that you have. But kVps, we're going to learn ranges of those, and those will be pretty consistent. The source to image receptor distance, again, is the only primary exposure factor that is not set on the control panel. So this is set in the room. The most common are 40 and 72. So that's what you need to know for testing purposes. 40 and 72 are the two standards. In our rooms, at the upright wall bucky, I know she's just letting you use it where it locks in because that just simplifies things with that room. It hopefully will let it sense the size of the detector so that your collimation opens up correctly. It should help with making sure that your alignment is correct. So just know that 40 and 72 are the standards. And so you say, well, really the more distance, generally, the better, because we'll talk about this towards the end of the semester, but it reduces magnification when you have greater distance, which improves spatial resolution, which is a good thing. But we can't get 72 inches over a table, right? It's impossible. It's physically impossible. So that's why years ago they just said, okay, 40 is going to be the standard, because you can pretty much get 40 inches in any x-ray room. So, okay, so this one, so far, let me see if I said this here. I didn't, but you can add this little sidebar here. KVP does have a direct relationship to exposure, like to the number of, photons that are created, and it's not proportional though. It's just direct, which means if KVP goes up, then the number of photons that is created goes up, but it's not proportional like mass and time were, or MA. So it is a direct relationship. So KVP has a direct relationship to the number of photons produced and to receptor exposure, but it's not proportional. We'll talk a little more about that in a few weeks. So when we look at source to image distance, it is the only primary factor that when you increase it, it decreases receptor exposure. So far, if we increase MA, we increase receptor exposure, right? If we increase the time, we increase receptor exposure. If we increase the combination of those two with mass, we increase receptor exposure. If we increase SID, it's going to decrease receptor exposure. And the reasoning of that we'll get into with the inverse square law. Okay, so I'm not going to get too much into that, because again, this is just supposed to be an intro to these things. We're going to dive into these things really specifically in the next few weeks. Okay. What questions do you have so far related to technical factors that we're setting, like on the control panel or the x-ray production or anything else, equipment related, whatever? Anybody have anything? A lot, huh? Okay. Well, if you come across something that you don't understand, then please, send me an email. I can certainly try to help clarify things. Don't be afraid to ask questions in here, because somebody else might be thinking the same thing or have the same question. So if there's no questions, then that's it. What time is it?
8:51.
8:51. So we're done early, done a little early here. I do have meetings scheduled with a couple of y'all, I think, so we can go ahead and run down and get those. Those are just the check-in meetings that we're doing here to see how things are going for you. So we can get those done. Otherwise, you guys can stay in here, because you'll be having, Yolanda will be coming up.